A Caylee table is a great way to study the structure of a group and also to convince ourselves that we are looking at a group to begin with. So in this video, I want to spend some time just looking at this Caylee table and talking about the different properties of this particular group of symmetries of the square. And some of the things we're going to talk about are going to be generalizable to working with groups in general. I did a little bit of cleanup. I got rid of some of the things that I'd written up before so that we can focus a little bit more on what's essential here. So the Caylee table that you can see up at the top, this is called the Caylee table for D4, is a very nice way to organize the operation in a group. We want to know what happens when I combine two elements in my group, and any two elements. And so here we have our 8 times 8, 64 different ways that we can combine two elements in our group. Now, I'd like you to look at this table and just jot down some of the things that you notice. What are some of the things that you notice? What are some of the things that you're wondering about? So you should pause the video and just to yourself study this table and then come back and you can listen to me mention some of the things that are important to study. Okay, so what are some of the things that you noticed? One thing that you might have noticed looking at this table is that the first row is just a copy of our entries at the top. So it's just a copy of our list of group elements in the exact order. So we have R0, R90, R180, R270, and then we have our 4 reflections. And the same is true for the first column. What is that telling us? That is telling us that when we are taking R0 and combining it with all our other group elements, we are just getting our group elements back. And no matter if we do R0 composed with something else or something else composed with R0, what is that telling us? Let's write down some of these observations. Well, it's telling us that R0 is the identity element in this group. So R0 is the identity element. Because R0 composed with anything is just that anything. And that's also true about the anything composed with R0. And that is the definition of the identity element. What else did you notice? One thing that you may notice, well, actually one thing that you may not even have noticed that you noticed, is that everything in our group, anything in our table, every group element in our table is actually a group element. So every entry that you are seeing is a group element. So let me write that down. Every entry in the table is a group element. And that shows that our group is closed under the operation of function composition. So we have closure under function composition, our operation. If all of a sudden we were looking at this table and we'd see a rotation by 200 degrees, for example, then that is not a group element. So if we happen to see something like that, then our group would not be closed under the group operation. But in this case, we are only seeing things that are in our group, so that means we have closure. So that's two important observations. A third important observation is that you might have made is that you will see R0 exactly once in each row and in each column. So R0 shows up once in each row and column. And that helps us to find the inverses of our group elements, of our symmetries. So for example, let me get green right here. Where do we see an R0? Let me grab R0 right here. So we see it right there, and that tells us that, what does it tell it? R90 composed with R270 is R0. So R90 composed with R270 is equal to R0. And if we look at the other order, R270 composed with R90, let's find that as well. R270 composed with R90, that is also R0. So that means R90 and R270 are inverses of each other. So we could use this to find inverses of everything. So R90 inverse is equal to R270. That's one thing that we found, and we could also list all of them. So R0 inverse is R0. Which one have I not noticed yet? R180 inverse is R180. You can find that in the table. And then all of our reflections are their own inverses. So H inverse is H, V inverse is V, D inverse is D, and D prime inverse is D prime. I mean, that's not all that surprising, since when you flip and you flip again, you're back in the original position. So those are three important things. Actually, these are all our group defining properties of our group. We haven't talked about associativity because associativity is not that easy to see, and we'll see in some other examples how we're going to deal with associativity. But one other thing that we can see right here that I want to point out is our table symmetric? Do you see any symmetry? Do you see symmetry, especially symmetry about the diagonal? That's what I'd like you to pay attention to. And you'll see that you see it at some places, but you don't see it everywhere. It's actually not symmetric. And that means that our group is not abelian. So we are looking at a non-abelian group. And it's a great example of a non-abelian group. So we don't have commutativity. And for example, let me give you an example right here. Let's see. What if we are looking at H composed with R270? And that's not the only example, it's just one that we could look at. So let me reuse green for that. I'm running out of colors. So our H composed with R270 is sitting right here. And the question is, how does it compare to R270 composed with H? Let's find that as well. So R270 composed with H is over here. So you see, it's like opposite of the diagonal. It's across, it lies right across the diagonal. And H composed with R270, that is D prime. But R270 composed with H, that is D. Those are not equal to each other. They are both diagonal reflections, but over different diagonals. They are not equal to each other. And so since these are not equal to each other, our operation is not commutative. And since the operation is not commutative, our group is non-abelian. So those are some of the things that we can find out just by studying the structure of our Caylee table. And so my recommendation is, when you encounter a new group, a finite group anyway, so a group with finitely many elements, and you don't have too many of those, start by making a Caylee table. Start by making a Caylee table. You learn a lot about how the operation works. You get some practice with the operation, and then you also have just a very nice way to learn about the structure and find the identity element, find inverses, convince yourself that the group is closed under the operation in question. So it's a really, really nice tool to start studying a new group.